All right, good afternoon, everyone. Welcome to UIS Math Colloquium. Today, our speaker is Professor Frank Morgan, Atwell Professor Emeritus at Williams College. He served as Vice President for two of the largest mathematical associations, and one is the AMS, another is MAA. So he served as Vice President for MAA from 2000 to 2002, for AMS from 2009 to 2012. In addition to his vast contributions to mathematics, his work in co-founding and mentoring one of the largest and best-known math undergraduate student research program has a profound impact on the mathematical society. He mentored over 100 undergraduate students. He showed them what's beyond taking math classes. He also showed them that students themselves are able to create original and rigorous math. His students are motivated and empowered to continue their own journey in mathematics. And I was lucky enough to be one of the students in his geometry group in 2010. And now today, I'm very happy to have him here in our colloquium. And without further ado, let's welcome Professor Frank Morgan to tell us about geometry of soap bubbles.
Oh, thank you very much, Ife. Yes, I was lucky too to have you as a student. So thank you for that.
You're welcome.
It's great to be here today and have this chance to talk about some recent breakthroughs on multiple soap bubbles. But first, we'll start with a single bubble, which you know is round. And so it has the least surface area for the fixed volume of air trapped inside. This was proved mathematically by Schwarz back in 1884. And similarly, a soap bubble cluster looks for the least area way to enclose and separate several regions of prescribed volumes. So separate is important there. You're not allowed to lump them all together and put them in one big sphere. That would be cheating. You have to keep them separated, and so they cluster around each other. And you still want to, this goal is still to minimize the surface area. For a long time, I have a question for you. We're going to start with a question for you guys. Do soap bubble clusters actually find the least area shape? So there are three possible answers here for you to pick. And now, even though no one can see you, I'd like you to raise your hand when we get to your answer. So how many of you would vote A, yes, soap bubble clusters always find the least area shape? Raise your hand. Or B, no, not always. Raise your hand. Or C, no one knows for sure, which is usually the right answer in mathematics. Yeah, but in this particular case, the answer is no, not always. And you can see that here are two 5-bubble clusters with the same 5 volumes.
Usually show
the only difference is where
there.
Sorry, I didn't get that. Did you hear that, Ife? So what someone said? I don't know. Okay, so the only difference here is where the tiny 5th volume is placed. And you're welcome to interrupt me and ask questions in the chat or by speaking. You have to unmute yourself. So the only difference between these two is where the tiny 5th volume is placed. On the cluster on the left, it's placed comfortably among the larger bubbles. And the one on the right, it's less comfortably placed among the medium-sized bubbles, with a result that the cluster on the left has a little more area, and the one on the left has a little less area, and the one on the right has a little more area, and therefore fails to find the least area shape. So that's not always. There's a counterexample. Is the one on the left least area? Well, no, it's actually better to put that tiny 5th region in back with the 3 largest bubbles. And then would that be the best? Would that be the least possible area? Well, I think so, but it's hard to know. I mean, maybe someday, how do you know that someday someone won't find another arrangement that does better? So it's very hard to answer questions like this. In fact, for a long time, my favorite open question was whether the standard triple bubble that you see here, that you always get when 3 bubbles come together, is really the absolute least surface area way to enclose and separate those three given volumes of air. Yeah, until finally we realized that we didn't even know if the double bubble that you always get when two soap bubbles come together is the least area way to enclose and separate two given volumes of air. Now, we mathematicians thought we knew this as a fact, and we asked this poor undergraduate, Joel Foisey, as part of his undergraduate thesis, to write down the proof. But as we talked to the mathematicians around the world who knew how to prove it, turned out that they didn't. And I asked Joel what it was like to see this, what first appeared as a conjecture in his undergraduate thesis, attract so much attention around the world. And this is what Joel said to me.
And then I started hearing reports about how progress was going. It was exciting to hear that people were making progress on it, and I was happy. A small part of me was a little bit envious isn't the right way of word, wistful of wanting to participate and be part of that.
Of course, he was an important part of it right from the beginning. And since then, he's had his own group of undergraduates at SUNY Potsdam working on new open problems. Now, that's a beautiful conjecture, right? Look at that lovely shape that you always get when those two bubbles come together. Two separate bubbles are wasteful, right? Because when they come together, they can share that common wall, and that's more efficient. And what else could a double bubble look like? How could anything else be possibly better? How about a bubble inside a bubble? Well, that's even worse, because when the inside bubble comes out, then the outside bubble can get smaller. And then they can come together and do even better. So this is why you never see a bubble inside a bubble. Well, actually, I had one 2 years ago when I was giving a talk in China. Look at that. There was a bubble inside a bubble briefly, but it's an unstable kind of thing. And as soon as the inside bubble comes in contact with the outside bubble, it just pops out. So it's an unstable thing with a lot more extra area that you don't want. But there are other possibilities.
Does it pop the outside bubble as well, or is it only the inside, the smaller bubble that pops?
Neither bubble pops. It just moves out and turns into
a standard
double.
Yeah, okay.
Yeah.
Oh,
it turns
okay.
into a standard double bubble. So when you see me sometime, we'll do a demo for you. We can do it, but it's hard to do.
All right.
Yeah, but good question. Now I'm going to show you, though, another weirder possibility. This is a computer simulation by John Sullivan. Are you ready for this? A non-standard double bubble. So here it comes. Wow, there it is. There's one bubble on the inside, and the other bubble wrapped around it in a torus shape, like an inner tube, as if the inside bubble is going to go swimming. And it turns out this is unstable, has more area than the standard double bubble. So it certainly doesn't disprove the conjecture. But it does make you realize that there may be other possibilities that neither we nor the bubbles have thought of yet. Here's a better picture where you can see inside and see how narrowly the waist of that center bubble gets squeezed by the toroidal inner tube that goes around it there. Well, if that could happen, maybe that blue bubble at the center with the red inner tube around it could have a second part to it, a skinnier blue inner tube going around the red inner tube, going around the central bubble. Connected, if you like, by some thread of negligible area. So connectedness it's not something you can insist on. And if that could happen, maybe you could have layers of bubbles on bubbles on bubbles. Or maybe it could break up into, or maybe you could have knotted bubbles. Maybe the bubbles could be knotted around each other somehow. Or maybe it could totally fragment into thousands of pieces, maybe even with some empty space on the inside. So this is kind of the low point of the talk. It's looking kind of impossible to prove anything because it's so difficult how could you eliminate all these possibilities? But the good news is, fortunately, we did eventually prove this. This was the announcement in Science magazine back in 2000 that the standard double bubble is best, better than any of these crazy alternatives. And one of my co-authors was one of my former undergraduate research students, Michael Hutchings, who's now a professor of mathematics at the University of California at Berkeley. Now, I'll say just a little bit about the proof, because this will be useful when I'm talking about the recent breakthroughs a little later on. So the starting point was that the minimizer, the ideal double bubble, has to be a surface of revolution about some axis. So here you see the kind of possibilities that might occur. And then Michael Hutchings realized that, first of all, you could deduce that that means it is a central bubble with tori around it, with tori around them, with tori around them, finitely many stages. And moreover, he realized that you could generalize the argument to limit the number of components and actually prove that for a double bubble in three-dimensional Euclidean space, there are just 2 or 3 components. So it would look something like the bubble on the left or like the one on the right, but it wouldn't have to be that symmetric. It could be kind of lopsided. But those are the only 2 kinds of possibilities. And then the hard part of the argument was showing that they can't occur because they have instabilities. That is, you can deform them a little bit, they want to do this, and reduce the area. I remember there were 6 hard cases according to how lopsided the bubble was. So these are the 6 cases. I labored over them for a long time. But anyway, we thus eliminated all the other possibilities, proved that the standard double bubble was best. And right on our heels, my undergraduate research group proved the same thing for bubbles, for hyperbubbles in 4-dimensional space. And this was considerably harder. It was no longer true that there were at most 3 components as before. In fact, the blue region could have any number of components. So that made it much harder. As I think instead of 6 hard cases, they had something over 100 difficult cases. So I asked Ben what it was like working on that team. This is what Ben had to say.
I wrote down all the possible alternatives, 200, eliminated them individually or in small groups to leave just 2 or 3 unresolved problem cases. But instead of finishing the proof off, the next week I got more ambitious and tried to classify general cases in higher dimensions. I eventually found a single case in R5 which could not be eliminated by our method.
Yeah, got stuck in R5. This example, it was just so lopsided and tilted that the earlier proofs broke down. So that was a barrier for years until a graduate student, Marilyn Daly, found a way to eliminate this case in 2005. But then she got stuck on other similar cases, and she finally gave up on the problem altogether. But Ben kept working on it, and a few years later, he proved it in all dimensions. So they'd done it in R4 before, R5, R6, R7, all dimensions. And as the dimensions got higher and higher, it was possible that there were more and more components. And so he found an argument that didn't depend on any component bounds, which would work for any number of components, any number of layers of tori on tori on tori. It was a very ingenious argument, a real tour de force, and it's never been extended by anybody else to any other spaces other than Euclidean space. So you know there are 3 most important spaces: the Euclidean space, the sphere, and hyperbolic space. And so, for example, the double bubble conjecture remains open in hyperbolic space in all dimensions 3 and above. So if you want to know more about this, you can read about it in my geometric measure theory book. The latest edition has my mom and me on the cover. And my mom's actually here to talk today, and she says, hello, everybody. Yeah. So back to my favorite open question, is the standard triple bubble the absolute least area shape? Well, there were, over the past several years, there were some hints of progress, but to look at those, to see those, we have to leave Euclidean space and go to another space. And I don't know whether you know this, but there's one space which is much nicer than Euclidean space. And I'm not talking about the sphere. This is the nicest space, but you may not even have thought about it. And what it is it's Euclidean space that has Gaussian density. So it's a space where the density falls off exponentially, a space where most of the mass is concentrated around the origin, and the space becomes very rarefied as you move away from the origin. And this space just has so many applications, including, by the way, Perlman's 2002 proof of the Poincare conjecture. So a very important space. Now that constant out in front of the density there is chosen to make the total weighted volume of the space, the total mass, equal to 1. The density falls off so rapidly that there's a finite amount of mass. That mass is 1. And this is something that makes it much nicer and simpler than Euclidean space with infinite volume, which is always a problem when you're working on these problems. To have to deal with Euclidean space that has infinite volume is a big problem. This space has total weighted volume 1, which makes it much nicer to work with. Okay, so what is the best single bubble in Gauss space? Now, at first you might think this should remain very easy because everything is still rotationally symmetric. And so the solution ought to still be a sphere. The problem, just so I'm sure I understand this, is to enclose given weighted volume with minimum weighted perimeter. So this density applies both to the volume, which might make you want to be near the origin where you can pick up a lot of volume, but with minimum perimeter, which wants you to be far away from the origin, so you don't know what you want to do. And the solution, which you'd expect to be a sphere just by symmetry, is not. It's not a sphere about the origin, but it's something simpler. Now, what could be simpler than the sphere with its constant curvature? What could be simpler than that? The answer is a plane, or in higher dimensions, what we call a hyperplane. Now, you'd say, a hyperplane, how can that minimize area? Well, its area is finite because of the way the density falls off so fast. So the hyperplane has finite area, and above it, there's some finite volume, some fraction of the total volume, which is only 1. So it encloses, and it turns out to be the least area way to enclose that amount of volume. Can't beat that hyperplane. If you want to enclose less volume, you just move the hyperplane up. If you want to enclose more volume, you just move the hyperplane down. It's not unique. It wouldn't have to be horizontal. It could be vertical. In fact, it could be at any diagonal angle. So, but that's the solution. And this idea of density is something that Yifei actually studied with me as a student in those days she was talking about. You see, this is their paper that was published. The title you can see mentions isoperimetry with density. And Yifei won a 2010 Math Fest Outstanding Student Talk Award for a talk she gave there. All right. Well, yeah. So there you see in the lower right that picture. She's in the far right. And here's an enlargement where you can see her back there in those early days. Looks just like now. Yeah, you'd recognize her. Right.
That was fun times.
Right. Good. Cool. That was a fun time. There we were at the picnic table in the science quad at Williams College, right?
Right.
So, but now back to, so the best single bubble in Gauss space is that hyperplane. And of course, I asked my students, what is the best double bubble in Gauss space? And it turns out that it's not two hyperplanes, which is a great way of separating two volumes from the rest of the space. But that is not the solution. It turns out that it's better to have 3 half hyperplanes meeting at the origin at 120-degree angles. And now, meeting, they wouldn't, So if they do actually meet at the origin, then they would all have equal area of equal volume of a third. They would all have equal volume of a third. Suppose you wanted to make the bottom region bigger, you might think you increase the angle, but that's not the way to do it. The way to increase the amount of mass in the bottom region is to just move it up so that it includes more of that neighborhood of the origin where all the mass is concentrated. And in fact, by just translating this shape, this Y shape around, you get all possible volumes. So that was the conjecture. That was the conjecture. Yeah, go ahead.
So this for double bubble, so that would mean any two of the three regions.
So, right, this is the double bubble. So that means there are two regions that use up part of the space, and then the third region there is just what's left.
Okay.
So you need for a region of a third and another of a third, and then you have to leave a third not enclosed. So yeah, okay. So when you're in a space of finite volume, a double bubble, you got to remember, even in Euclidean space, a double bubble, there are really three regions, right? The two things inside the bubble and the outside of the bubble.
Right, yes.
You have that. A double bubble, there are three regions, the two regions in the bubble and the outside of the bubble. Yeah, good. So translations cover all possibilities there. And the students using the methods that were already known, which worked in Euclidean space, worked here as long as all three regions had about the same volume, about a third. I mean, for example, if they were all between 0.3 and 0.37, then that would do it. And the reason for that is that in that case, the known component bounds were stronger. We knew that each region was connected.
Was that Alan Scott?
Sorry?
Right there? Is that him? His class, Alan Scott. Mr. Scott, is that his class? Yeah. I have to talk to him. Okay, go try
to. Yifei, could you understand that? I'm sorry, I couldn't.
Yeah. I don't think that's a question.
Yeah.
I couldn't.
Okay, well, good. Good comment there, maybe. Sorry, I couldn't understand it. So, oh yeah, but here, Rudy remarks to everyone in the, that this meeting at 120-degree angles is also what happens in soap bubbles. Soap bubbles come together at 120-degree angles. So very good observation. Yeah, that's a very fundamental kind of rule. We like that thing. They meet at one, that's a very efficient way to come together. So just these very special volumes were done. And the case of proofs for all volumes, it was clear would require some completely different approach. And no one had any idea how to do anything. So now we have to wait 15 years. And here's some news. Just last year, Emmanuel Milman of Technion in Israel and Joan Neeman of the University of Texas in Austin proved that this Y shape is the best double bubble for any volumes. So that was a major breakthrough. And let me just give you a bird's eye view of how the proof goes. It looks at how the least perimeter or surface area depends on the three volumes that you're given. And we know what that is for the Y shape, meeting at the 120-degree angles. We know what it is for the Y shape, so that's piece of Y on the right. But we don't know that that's the minimizer. The minimizer, which I've could be more complicated, could be curvier, and its perimeter, which I called P0, depending on the three volumes, all we know is that it has to be less than or equal to Py, because it's the minimizer. And so if you'd graph it, the blue curve would lie under the red curve. And they come together at the ends where one of the volumes goes to zero. That's easy to check. All right, so that's the starting place. And now what was the proposition that they proved? They proved that the curvy one on the left is less stable, has a more negative second derivative than the one on the right. But now look, that isn't what the picture looks like. In the picture, it looks like the red curve has the more negative second derivative. And the only way that both of these things can be true is if the two curves actually coincide and the red Y is the minimizer. But the proof was much more technical than all that. But that's the bird's eye view. And they proved more than that. Their proof worked not only for the double bubble, but for the K bubble. Triple bubble, quadruple bubble, quintuple bubble, all of them. And the answer in general is the so-called cone over the regular simplex. Let's just think about the triple bubble in R3 is the cone over the tetrahedron that you see here. And the four faces correspond to the three regions and the outside of the bubble. And they all come together at that red dot. If that red dot is at the origin, then all four regions would have volume a quarter. And if you want the bottom region to have more volume, you just move it upwards. And once again, translations cover all possibilities. And another nice feature that remains here is that these are meeting like in soap bubbles. And you notice that every region is adjacent to every other region. So it's kind of as central and together as it could be. Very desirable feature. Yeah, so that was a momentous development. I'm not going to say much more about the proof. The first step was showing that all of the pieces are flat. All the pieces are flat. And the method was, if a piece isn't flat, so if it's a little curvy, then you show how you can deform it a bit to make the area go down. And that's not so clear. I mean, if it was very wiggly, maybe you could do something, but if it's just bulging in one direction and you aren't allowed to change the volumes, it's not clear how to do that. And the operation also were many technicalities requiring the latest results on how nice or regular these surfaces have to be. So it was also, it required lots of ideas and lots of technical prowess to prove this result.
I think Carter has a question.
Carter has a question. Yes, Carter, go ahead.
Okay. Okay, so I guess like my question is that like I'm trying to figure out the exact I guess like the challenge we're doing. So is it like basically we have like a certain amount of area, right? Like the thing above is like we have a certain amount of area we want.
You're given 3 volumes, yep. You're given
Okay.
3 volumes, and you want to enclose and separate them.
Okay. So like you have like 3 so like you want 3 bubbles, each with a certain volume, and you want them to like cover the minimum like surface area or like
Yes,
I guess.
exactly right. Yes, good,
And
Carter.
while each of them have a specific volume.
That's right. You're given the volumes. Yeah.
Okay. So like that's why that's what I have to do with the whole moving the point up or down that way you like have a way to like arbitrarily adjust the sizes of the
That's
bubbles.
right. That's right. By moving the cone over the tetrahedron around, you cover all volume possibilities.
Okay.
So in this picture, it looks like all the volumes are the same. That would be true if the red dot was at the origin. But if you move it up, then the bottom region would have more volume and the others would have less volume. And you
Okay.
just move it around, you can cover all the possibilities.
Okay.
Now,
Thank
the tetrahedron doesn't fit in the plane, and the fourth simplex doesn't fit in 3D, and so on. So this only applies if the dimension is as big as the number of bubbles that you want. And so, for example, although we know the best triple bubble in R3, we don't know the best triple bubble down in the Gauss plane. And here's what's conjectured. This is a good student project. This is what is conjectured. It's conjectured to be a double Y. So lots of 120-degree angles, and you can get all possible volumes, or here where they'd be areas, by just moving it around and changing the length of the central bar. So there's a conjecture which remains open today. Okay, finally now back to Euclidean space. That was just some of the progress in Gauss space. But now we go back home. We're back in Euclidean space. And we return to this, our favorite question. Is the pictured guy here the best triple bubble? Does it look like that? And now comes the big news. just last year, Milman and Neeman went on to post a proof, not published yet, of the triple bubble in R3 and above being just what was predicted. So it is, that was a major thing. It hit all the news outlets. Here was the article reporting it in Quanta magazine entitled Monumental Math Proof Solves Triple Bubble Problem and More. And that word monumental is actually a quote from me, although it's taken out of context here, as I'll explain shortly. And the and more, what does that mean? How could you do more? They did it in all dimensions. Well, by and more, it turns out they also proved the quadruple bubble in R4 and above, and promised to, and just succeeded 2 months ago in proving the quintuple bubble in R5 and above. And they did all of this not only in Euclidean space, but also in the n-dimensional sphere, not hyperbolic space, but also in the n-dimensional sphere. So this was really a completely remarkable accomplishment. And I just want to say a little bit about the proof. I don't want to say too much about the proof here, but the first step in the proof, a huge step, and the part that I called monumental, was to show that the surfaces are all spherical. And for example, that's enough to immediately prove the double bubble. So that's a gigantic accomplishment. And it's much harder than back in the Gaussian case. Remember, we just had to prove that the surfaces were flat, have curvature 0. But a sphere can have any curvature. You can have large spheres, which are almost flat. You can have small spheres that have very large curvature. So that was a very difficult step. And even after they proved that, they still had to prove that each region was connected and didn't have many pieces to it. Remember back in Euclidean space, when I first mentioned Michael Hutchings and his early lemmas showing connectedness, well, this comes much later in their argument. It's harder. And even if you get connected, when you have lots of bubbles, it's still hard to show that each region is adjacent to every other region, which is the simplest kind of configuration that you would like. So for example, you don't want them all spread out. Like you would know in a triple bubble in a 1D chain like this, or a quadruple bubble in a 1D chain. And although that's manageable for triple bubbles and quadruple bubbles, that's what makes it so impossible to work with more than bubbles. Just in higher dimensions, when you have lots of bubbles, there are just so many ways that they can fit together. The number grows exponentially, and it just seems impossible to prove which one is best. Yeah. So the open question that I want to leave you with is about the quadruple bubble now. Triple bubbles settled in all dimensions, but the quadruple bubble, proved only in R4 and above, is open in R3. Here's what we think it looks like, just kind of what you'd expect. But their proof doesn't work because there's no reflective symmetry. It's just not quite symmetric enough for their proof methods to work. So that's open. It's only proved in R4 and above. And it's also open in the plane. So the best quadruple bubble in the plane, we think it looks like this one on the left, which has been proved when all 4 areas are equal. So that's the picture here. There are 4 unit areas. It was proved by Paolini and Tortorelli in 2020, proving that it was that, and not one of these things on the right, the top one on the right, where one of the regions is in the middle, surrounded by the other 3, or the one in the lower right, where the first region has 2 components, one at the bottom and one at the top, and then there are the other 3 regions. And the picture on the left, it looks like those spokes going out are straight, but they aren't actually. They bow a bit into the bubbles E1 and E2. And so those bubbles are not convex. It's nice to have convex bubbles. So the people working on this said, well, maybe if we chose the areas correctly, we could get all of the bubbles to be convex. And this is where the student who was the high school student, 9th grader working with me last year, Marcus Collins, and he's here at the talk today. Oh, but I think oh no, he's still here. there he is. We can see him out there in the audience. He's sort of frowning, but he's very modest. Yeah, so he looked at this and he did calculations, and he discovered that the largest bubbles are always on opposite sides of the central edge, and hence they're never convex. You can see it clearly on the left there. The top bubble, it's not always bowing outward. It's sometimes, so it's not always convex. And the way he studied this was using computations on Brache's evolver. So he would put in some rough polygonal shape and then just let the evolver try to improve it. And you wait and you watch, and the evolver moves, it keeps it moving until it's happy and thinks it's in the best possible configuration. Looking something like that, with that wonderful central bar in the center. And he also looked at densities like R squared. This is very different from the Gaussian density, which, remember, got small as you go far from the origin. This gets larger as you move away from the origin. And he found, using the Brache's evolver, that in this case, the quadruple bubble is even more beautiful. Instead of having that bar in the center, everything collapses to a point, and it gets completely symmetric. A beautiful symmetry that doesn't occur in the Euclidean case, only occurs in this case of density R squared. And finally, I want to show you. So let the Brache evolver work on the Euclidean solution with that density around, and you'll see that the bar in the center just gradually fades away. This is a difficult computation because all the action is around the origin where the density is 0. So it's very hard for the Brache evolver to do it, but Marcus got this to work, and there you get that beautiful symmetric solution in the Gauss plane with density R squared. Well, there are lots of open questions around, but the ones I want to leave you with are the two I just mentioned of the quadruple bubble in R square in three-dimensional space and in the plane, where we're pretty sure what we know the answer ought to be, and we just don't know how to prove it yet. So I'll leave you there. Thank you very much.
Thank you. Thank you for the wonderful talk. So now it will be time for question and answer. You can type your question in the chat or just unmute and ask your question.
That's right.
The ending with like the bubbles and the section before.
Well, there was the section on Gauss space, and then we came back to Euclidean space for the triple bubble.
Yeah. I guess it was like the section with the 2D ones, like just before the ending.
Oh, yeah. So let's go back to, yeah. So here's 2D, the best quadruple bubble in 2D. The conjecture is that it always looks something like the one on the left, which was only proved for 4 equal areas.
Okay. So is it like, so it's only proven if the areas are all equal?
In the plane, the quadruple bubble is only proven for 4 equal areas. That's right.
Yeah.
Although Marcus did some experiments on the Brache evolver, so we think we know what the solution is for lots of different areas.
Okay. So
But only proven for equal areas.
So is that basically like they managed to like find a way to like they made a system in order to like get the other like try and find other bubbles? Like
Well,
optimal bubbles?
yeah, so how would they prove something like that? Well, first of all, you want to prove some kind of symmetry. And you notice this has a very nice up-down symmetry, and it has a nice left-right symmetry. And that's something you might expect when all the areas are equal. If you can prove that, that's a big part of the proof. So Monica here, I noticed in the chat, asked, do you think it could be applicable to explanations involving multiple universes? Now, multiple universes don't usually have much to do with each other. Whereas in the multiple soap bubble, we see all the bubbles coming together, being adjacent to each other. So they're kind of opposite phenomena. There are bubble theories involved with the universe, but not exactly related to anything I did today. But the thing is that the structures that occur in compound bubbles are very efficient structures, and we see them throughout physics and the universe. Mathematicians' approach to understanding complicated objects is to start by looking at simpler ones. And so if you want to understand the geometry of the universe, you should probably start with the geometry of the soap bubble cluster. Maybe computation could be applied, certainly to this problem, as Marcus was doing, applying computation. For multiple universes, it's really a very theoretical thing, and I don't see how computation would help much. Here's a question from Rudy. When you had one bubble inside another, the little bubble moved out the bigger one and none popped? Correct. Maybe you can try that yourself. This is hard to do, but it's easier if you use a straw. So sometimes you can get a nice bubble, have someone hold it for you using their wands, and then take a straw and blow a little bubble on the inside, and you'll see it just goes to the wall, and then it moves outside without breaking and stays attached. Yeah.
Does the bigger bubble shrink a little bit because that volume came out of it?
Yes, exactly right. Yep.
So it stays attached to the bubble. It doesn't like float away.
That's right. It becomes a standard double bubble. It's just, right? Think about how the standard double bubble looked. So that was back near the beginning, maybe. We had that. Oh, do we have a bubble? The double bubble. Get to in a second here. There was that double bubble. So it would look a lot like, so it could, for example, here, the smaller one barely fits inside the other one, it looks like. But if it did, then when it popped out, it would look like this standard double bubble. To try that now, right? It's sort of a little hard for you to believe. Good, yeah, but it does. Stays attached, just moves out. Doesn't like being inside, but it likes being attached.
Have a question. I was asking about in the Euclidean space, the favorite ways for bubbles to meet is at the 120-degree bubbles, right? And in the Gaussian is the hyperplane, the flat, no curvature. What about in the R square? I think I missed that part. In the R square, what's their favorite way to meet?
They always like to meet at 120.
Also 120. Oh,
Gauss,
okay.
In the Gauss case, remember, it was 3 hyperplanes meeting at 120-degree angles.
Ah, yes. Right, yes. Okay.
In space, they come together at 120-degree angles. Yeah, they always meet at 120.
Ah, okay. That's interesting.
That's why it was so weird, that example at the end of Marcus's, where there were 4 lines meeting at the origin. And that's only possible because the density is 0 there. So that's a very exceptional thing.
Okay. I think that might answer the question Carter had. Oh, I think Carter was asking about something more general. What if in other type of spaces, then would it be always 120 then?
Yes, it's always 120.
Oh, right.
I guess I was like, I guess my question was most, hopefully this isn't rude. My question, I think, was that I was thinking about like if we could have like the Gaussian way of distributing like the densities. So like there probably are like other ways of like distributing densities, and like in that case, like are there like any like things for Babbel?
Yes,
Or
it's
like
very interesting. You look at there are a lot of other densities, some very important. I mentioned 2 today. I mentioned the Gaussian, and then at the end I mentioned density R squared. But no matter what the density is, the angles are still 120.
Okay.
That's because every space infinitesimally is Euclidean. In fact, that's how mathematicians define a space, something which in the very small looks like Euclidean space.
Okay, Rudy has another question.
Good.
Sorry.
Oh, what for?
what force is pulling on the bubble when inside the other that makes it want to pop out and make that 120-degree attachment?
Well, so when it's not touching the outer bubble, there's no force. So it could, wander around until it happens to touch. Now you're in this situation where you have two bubbles that are tangent to each other, right? And you can see how if they come together, two pieces of surface are replaced by one piece of surface. So it's almost like two pieces of tape wanting to come together. There's an attractive force there that makes them come together. Now, why does it pop out instead of in? Because if it's popping out, the bigger bubble can be smaller.
So is it like the air pressure from the outside is sort of pushing the bigger bubble smaller?
Yes,
Or is
the
it?
air pressure inside the bubble is bigger than the air pressure outside. That's right. And in fact, it would have to be to balance the curvature. If it weren't that case, the bubble would just collapse, right? So the pressure has to be bigger inside than outside. And in the smaller bubble, the pressure is bigger than in the big bubble.
One last question from me. You had a picture of where you have a string of bubbles, like 3 bubbles in a line or 4 bubbles in a line. Is that stable, or does it just try to come together into the cluster?
It's marginally stable. So that, for example, if the bubble at the end rotates around the bubble adjacent to it, the surface area doesn't change. But by the time it gets all the way around, when it bumps into the other bubble, now it finds a way to do better.
I see. Okay.
Stable, and so those kinds of cases can be hard to eliminate.
Okay, I see.
I kind of like this picture here. I can see all of you now better.
Dr. Morgan?
Yeah, hi.
I have a question. It's a little bit self-service. And we also have some Illinois middle school teacher in this room. So you are clearly a master teachers. I watch a lot of your video on YouTube, and you have won numerous teaching award. As you may already know, that UIS is a teaching-oriented institution. So can you share your insights and your teaching tactics you used that could help all of us, actually, as we mentor either undergraduate students or pass along information in our work?
Well, thank you. We have a big advantage in that what we're teaching is mathematics, which is so inherently fascinating if you aren't in a big hurry with it, right? Sometimes if you feel under some pressure, math can be very frustrating because it goes very slowly. But if you can just play with it and enjoy it, it can be so satisfying and fun. That Marcus Collins that I showed you at the end, he was a 9th grader last year when he did this work. So that was really completely remarkable. He has this written up. It's really a good paper, worthy of publication. And I'm very proud of what he did. But he took his time on it, but he was also very responsible. He kept at it. This, I think, is a secret in math, right? You don't have to hurry, but you have to work on something every day. And of course, the best way to learn math is by working on an open problem. Now, you might, people used to say, no, you can't do that until after you finish grad school. And then they said, oh, maybe you can do it during grad school. And then they said, well, maybe we can have undergraduate research. And now we have, middle schoolers doing research. But I think it's good for them to be really working on an open-ended problem because it makes them so much appreciate everything they learn. I've just seen this, students who do a little research and then you see them next year in class and they're transformed because instead of wondering, what is this good for? They're thinking all the time, oh, how could I use this? And that's what you want them to think as they're learning, right? How could I use this? I'd love to use this somewhere.
Thank you. Yeah, I think we probably would like to maybe in our classroom add some kind of project where the students take their own initiative in solving and thinking in the problem. That would usually help and boost their confidence.
Yeah, maybe, but I mean, that you can't have too high expectations. It's
Right.
math is very hard. And it goes slowly, but it's
Right.
also beautiful.
All right. Thank you very much for the advice. Do we
Thank you.
have any more questions? Okay, it's 2:01, and if we don't have any more questions, let's give Dr. Morgan another round of applause.
Well, thank you all very much. We're great. There were great questions. It was really fun being here today, and especially seeing you again, Yifei.
It's great seeing you again. All right. Hope you enjoy your time at the beach.
Yeah, boy,
All
we've
right.
got with the storm out there, we've got some
Oh.
wind and waves, and I think that may have done the internet in. I'm just using my phone right now. Yeah.
Okay. All right. All right. It's great having all of you here. Now let's conclude the session. And you can always email me if you have any more questions. And I can forward the question to Dr. Morgan if you don't mind.
Oh, that would be fun.
Right.
Thanks.
All right. All right. Okay. Thank you for coming.
Oh, thank you. Thanks. Bye.
All right.
Bye.
Bye.